Okay, we are looking at the 2.5 homework. So let's check this out. We are talking about continuity. So remember, there's kind of three things to check whenever you're doing continuity. Number one, the function has to be defined there. Number two, there has to be a limit. And number three, those two things have to be equal to each other. So this one we're just talking about, the entire graph from -2 to 7. So notice that there is a problem. -2 is okay if it's an endpoint. I guess my pencil must be dead. So if it's an endpoint like this one is, then the limit just has to exist from its the left or right hand limit. So in this case, the right hand limit. So notice at this spot where it looks like there might be a problem, if you plug in a -2, you get 1. The limit as you approach -2 from the right hand side is equal to 1, and obviously 1 is 1. So we're good at -2, 8. You would do the same kind of thing, except coming in from the left. So as you come in from the left, you can see that the limit is like 2.9. That's also what you get when you plug in the 7. I think I said 8, but and those are the same. So we're good to go there. So the only one we might have a problem with now, obviously everything in the middle is fine. There's no issues there, but let's check out this 4 right here. So notice if we try the first step of just plugging in the 4, it's undefined there. there's nothing there. It's a big hole. So this is not continuous at that particular point. And that point is x equals 4. So we've got a problem there. So the graph is not continuous at 4. All right, so let's check out the next one. This is the same type of question. So again, just check those places. It's asking about the interval from -1 to 3, which is, well, where the graph is. So remember at -1, that's an endpoint. So you just got to make sure the limit's there. And we're good to go on that one. I'm just going to make this a little bigger. All right, so -1 looks good. Notice if you plug in a -1, you get 3. The limit as you approach from the right to -1, you get 3, and obviously 3 is 3. But now let's look at right here at 0. Notice if you plug in a 0, you get, what, 2. However, if you think about the limit as you approach 2, from the left, it's going to 2. Oh, sorry, I meant as you approach 0. So notice coming in from the left, it's actually going to 2, but coming in from the right, it's going to 5. So the left and right don't agree with each other, which means there's not a limit here. The limit doesn't exist. So we have failed the limit part. So this is not continuous at 0. This is no good at 0. There's kind of a little corner spot at 1, but that doesn't that doesn't affect anything. 2 has kind of a little corner spot. We're good to go there. And then for 3, make sure, when you're doing that limit part of the check, it just has to come in. It's an endpoint, so just come in from the left there. And notice you get a 1, and if you plug in a 3, you also get a 1. So this one is not good at 0, and that's called a jump discontinuity because it goes from here and jumps up there. So no good there. All right, let's just go to the next one. So this is another one with the picture. So this is a piecewise function, and holy cow, it has 1, 2, 3, 4, 5, 6, 7, 8 different functions going on. And we've got to answer a bunch of questions here. So the first one just says, does f of 3 exist? So in other words, can you plug in a 3? And yeah, you can plug in a 3. If you plug in 3, you get 2, right? So f of 3 is equal to 2. I'm guessing the next question is going to be, does the limit as x approach 3 exist? And yes, it does. Notice as you approach it, you actually go to 4. Now, does 2 equal 4? No. So it is going to be discontinuous there, even though it exists and it has a limit. They're not the same. So it does exist. Oh, was that the only question? Okay. The limit exists. However, they are not the same. So see, it doesn't satisfy that third condition for continuity, so therefore it is discontinuous there. So it's got to satisfy, it's got to exist, the limit's got to exist, and those two things have to be equal. All right, so this is the same kind of question, so I'm just going to skip him. Same kind of question. So again, you're just checking those three things. Does it exist? So does f of 2 exist? Does the limit as, say, you approach 2 exist? Are those two things the same? All right, so this one we don't have a graph. We've just got the function. And so it wants to know about continuity. So it says, describe the set of x values where the function is continuous. So when you're looking for these kind of things with a rational function, especially, those jump discontinuities, those occur in piecewise functions. And I say that, but also recall that the absolute value is a piecewise function. This is equal to x for x greater than or equal to 0, and it's equal to the opposite of x for x less than 0. So absolute value is a piecewise function, so you will need to kind of check him to make sure he doesn't have anything. And then also those greatest integer functions, ceilings and floors, they can have jumps, of course. But in general, this is a nice function. The top is a polynomial, therefore he's continuous. The denominator is a polynomial, therefore he's continuous. So the only problem is that when we put them together, we have to make sure that that denominator is not 0. So let's go ahead and factor him. And so we would need two things that multiply to get positive 10 and add to get a negative 7. So let's go negative 5 and negative 2. So now look what happens to this function. Oh, actually nothing's going to happen to this function. So this is x squared, that's minus 7x. Okay, so nothing divides out here. So we do have problems. If x is 5, we have a problem, and if x is 2, we have a problem. So we're actually not allowed to be those things because that would give me 0 in my denominator. So we're going to say that this is continuous everywhere except at those two places. So recall how to take those out of interval notation. We're just going to go up to 2. Notice the parentheses because we don't want to include him. And then everything between 2 and 5 is good. And then everything bigger than 5 is good. So notice what this does is it removes the 2 because of the parentheses, and it removes the 5. So that's going to be our answer there. If there had been a divide out, then things would have been a little bit different. And actually, no, it wouldn't have, because it still would have had a hole there. So it really doesn't matter in this case. Let's see, union. Then we'll go from 2 to 5. Union 5 to infinity. And we're good to go. So we just took the 2 and the 5 out. All right, so let's look at this one. This one wants to know where cosine x over 2x is continuous. So again, just kind of the numerator is fine. Cosine x, remember cosine x just looks like this. He doesn't have any problems. 2x, of course, is just a vertical line. That was really bad. With a slope of 2, I said a vertical line, a diagonal line with a slope of 2. So individually, they're both okay. However, we've got to make sure that denominator is all right. And we can't have the denominator be 0. So let's try to set that 2x equal to 0. And that means that when x is 0, we get a 0 in that denominator. So we're not allowed to be 0. So again, we'll just have to pull the 0 out. And we do that like this. So again, notice those parentheses on the interval notation. That's what removes the 0. Okay. All right. How about this guy being continuous? Okay, so let's check him out. So let's look at the numerator first. So for the numerator, we've got 5x tangent 3x. This guy's okay. He's just a line. However, tangent is going to have a few problems. So recall the tangent function in general looks like this. He has asymptotes at negative pi over 2 and pi over 2 because he doesn't exist there. The reason is because tangent is sine over cosine. So what we're going to do is we've got to figure out where tangent 3x, if you recall, that affects the period. So let's look at how that tangent is going to be, what values we'll have to exclude because of that tangent. So let's just try to set, let's look at tangent 3x. Tangent is sine over cosine. So what we need to do is make sure that that denominator is not 0. Or in other words, figure out where he is 0 and take those places out. So if the cosine of 3x is equal to 0, then we're just going to, let's just think about that unit circle. Cosine is 0 up here at pi over 2. Cosine is also 0 down here at 3 pi over 2. And actually, every pi over 2 plus is going to give you a bad spot. So let's, so if 3x is equal to pi over 2 plus any multiple of pi, so we're just going to call that pi n. So pi over 2 plus pi, bad, plus pi, bad, plus pi, bad, plus pi, bad, or minus. All right, this is for n being any integer whatsoever. So let me just tack on, this is for n, an integer. This is where it's going to be equal to 0. So now we do need to get rid of this 3. So I'm just going to multiply both sides by 1/3 and see what happens. So we get that x is equal to pi over 6 plus, instead of multiples of pi, it's going to be multiples of pi over 3. So anywhere that it's pi over 6 plus any multiple of pi over 3, we're going to have a problem. And let's see, how was that written? It's got pi over 6. It has any multiple of pi over 6. Oh, duh, because we have some redundance here, right? This essentially ends up being any multiple of pi over 6. Since adding that pi over 3 gives you another multiple of pi over 6. So we'll just be able to say any multiple of pi over 6 is going to be bad. Okay, so there's that. Now we also need to check that denominator. So we need the denominator to not be 0 as well. So let's look at that denominator and try to see when he might be equal to 0. All right, so notice what happens here. We move that 1 over, and we get this -1. X squared can't be -1, so this never happens. We don't need to worry about this. Okay, I see what they did here as far as the definition goes. So let's look back at what we had written. So we had pi over 6 plus any multiple of pi over 3. So notice what this would look like. And this is where they're coming up with their definition here. So they're thinking, okay, well, this is pi over 6. And then they say for n being any odd integer. So notice that if n is an odd integer, then that'll get you the jump. Sorry, if you put in n, that'll get you a pi over 3 jump because it'll be a 2 jump. So that's why they had it written like this. I actually like this much better. So on the exam, if this comes up, I would leave the answer this way. But if you're not real sure what's going on, just plug in a few values for n, and you'll be able to kind of see what's going on there. So anyway, so we've got our answer here. I don't know why I spent all that time erasing, but we're going to be good everywhere except here. And again, if you want, just kind of plug something in. If you look at pi over 6, well, we know pi over 6 is going to be bad. That's where n is 1. So see, they're saying n is any odd integer. So if you want to just check a couple, now notice when you jump to 3 what that's going to do. So pi over 6 times 3 is going to end up being pi over 2, and that is your pi over 6 plus pi over 3, right? You see how that ends up being 3 pi over 6, which is that pi over 2. So anyway, convince yourself. But again, I do kind of like it. I know they kind of made it look more compact, but doing it with that plus any multiple of pi over 3 works just fine. All right, so let's look at this one. So now notice the 4x minus 5, the radicand there looks just fine. He is a line. He's good to go anywhere, except wait a minute. We're doing an even root. With even roots, you've got to be a little bit careful because you can't take the even root of a negative number. So we have to make sure that 4x minus 5 is non-negative, and so that means greater than or equal to 0. So we're good as long as we plug in, as long as we're looking at values that make this greater than or equal to 0. So we can just solve this. We'll move the 5 over and divide by 4. So as long as we plug in anything greater than or equal to 5/4, we're going to be continuous. Okay, and it says to do it, simplify. It says interval notation again. So remember, interval notation here, we're going to have a bracket because 5/4 is okay, and we're just going to go up to infinity. So make sure you've got that bracket on there. That bracket is because we're including the 5/4. All right, so now we've got our piecewise, which I'd already mentioned can be a problem. And it's a problem basically if you have one of those jump discontinuities, or if your function itself has a problem. So if we look at the individuals here, a 6 is just a horizontal line, he's fine. 10.5, just a horizontal line, he's fine. This one, however, has a denominator that we're going to need to check out. So obviously, if x squared minus 49 is 0, now be careful here. You can either factor this, it's a difference of squares, and then you would get the -7 and the +7. If you just solve it, so you just move the 49 over to the other side, and then square root both sides, do not forget your plus or minus, otherwise you're going to lose a value, right? So x is plus or minus 7. So you can solve it without factoring it, just do not forget your plus or minus there. So we know that this thing has problems at plus and minus 7, okay? Now we've got to figure out if a hole is created there, or an asymptote, that maybe is plugged by these other two things. So this is where we have to factor the top as well. So let me kind of show you how that works. That top appears to be a difference of cubes. 9 times 7 is 63, 28 and 6 is 34. All right, so that top is a difference of cubes. So if you recall, this factors into same, opposite, always positive. This factors like this. So for ours, that's going to look like this. So on top, we're going to have x minus 7, and then we're going to have x squared plus 7x plus 49. So this is how this one factors. You can check it if you want. And then we're going to divide that by, we already factored that bottom, it was x plus 7, x minus 7. So now with a rational function, if you have a factor that divides out, then that means there's still a hole in the function, but if you didn't kind of zoom in, you probably wouldn't even notice it. So if you were to graph this, I don't know what this graph actually looks like, but as you get close to 7, the graph is actually going to have a little hole there. But otherwise, it's going to look okay because that x minus 7 factor divided out. Now, at x plus 7, he did not divide out. You are going to have an asymptote here, a vertical asymptote. So 7 or negative 7 is going to be just bad. Okay, there's no way to fix necessarily an asymptote. So, however, let's see what we should make 7 in order to plug that hole. You see, so 7 really does not exist. You can't plug in a 7, but they say at 7 we're going to make it 10.5. So let's see if 10.5 plugs the hole. Okay, so if you look at the function we have right now, and plug a 7 into it, so we'd have 7 squared plus 7 times 7 plus 49 divided by 7 plus 7. All right, so this is going to be 49 and 49, which is 98. Oh, that's 49 times 3, isn't it? Seven squared is 49. 7 times 7. Okay, so that's that 343. And then 7 plus 7 is 14. And 343 divided by 14. Oh, that's not even close. Okay, let me make sure that I did my math right there. 7 times 7 plus 7 times 7 plus 49. Yeah, see, I wasn't even close, you guys. What was I doing? I was multiplying them all. All right, so the top is 177. And so then if we divide that by 14, I'm still not getting 10 and a half, you guys. All right, 7 times 7 plus 7 times 7 plus 49 divided by 7 plus 7, which is 14. Oh, it is 10.5. I don't know what's going on with my arithmetic here, but we do get 10 and a half. So what that means is, even though there was a hole in the original, the second part of the piecewise function is actually plugging that hole in with that 10.5 value. Okay. So that hole is plugged. However, the negative 7 is no good. So we're going to say negative 7 is the problem here. Because you can't plug an asymptote. How did I mess that up? Okay. It was negative 7, right? Oh, sorry. Yeah, I just chose the wrong one. It's it is continuous everywhere except negative 7. All right, so let's look at this one. It says find the following limit. Is he continuous at the point being approached? So we're looking at a limit. Our first instinct for the limit should be to plug it in and see what happens. But actually what we'll do is we'll go through the 3 steps. So first, we'll just call this f of x, and we'll see what happens if we plug a pi over 6 into it. If we can't even plug a pi over 6 into it. So cosecant is 1 over sine plus 12 square root of 3. Tangent is sine over cosine. Right, so it's going to look like this. This is just the inside. So let's see what this looks like. So pi over 6 is our smaller one down here. So he's square root of 3 over 2 1/2, which means the sign is 1/2. So if our denominator is 1/2 and then we flip it up, that's a 2. So we get a 4 here. So that's 1/2. This is sine, right? So that's a 1/2. Flip it, we get a 2. We square it, we get a 4. So then we're going to have 12 square root of 3. Again, the sine of pi over 6 is a half. Cosine of pi over 6 is square root of 3 over 2. So these 2's divide out. And then the root 3 is actually going to divide out. So we get 4 plus 12, which is 16. And now take the square root of that. So the square root of 16 is 4, which means that if we just plug in the value, so f of pi over 6 is equal to 4. Notice we didn't have any problems with that. There were no denominator issues. It wasn't negative. So because there was really nothing going on there, we don't have any issues. Now, if we were plugging in something where sine was 0 or cosine was 0, we would have had issues. But we weren't plugging in either of those. So the limit there is also going to be 4, and everybody's good to go. So this should just be the function is continuous. So that's going to be this one. So this was equal to 4, and the function's continuous. Yay. All right, so this one is kind of like that piecewise one we did, except this time we're going to plug the hole ourselves. So let's look at this function. Notice if you do try to just plug a 10 in, you're going to get 10 to the third minus 1,000 over 10 squared minus 100, and that would give you 0 over 0. So let's factor and see if 10 is a whole. Now, if 10 is an asymptote, if we have an asymptote at x equals 10, then we can't fix this, okay? However, if we have a hole there, we can plug the hole. So let's factor that top. That's a difference of cubes again. So it's same sign, opposite sign, and always positive. 10 squared is 100. So that's a minus b, a squared plus ab plus b squared. And then we're going to divide that by, the bottom is a difference of squares. So notice that the s minus 10s actually divide out, which means there is a hole at s equals 10. So again, I don't know exactly what this thing looks like, but when it gets to 10, there's a hole. Okay, so what I want to do is figure out where the hole is, and then I'm just going to plug the hole. So how do I figure out where the hole is? Well, I just plug the 10 in to where to the function after we divided out the s minus 10. So let's plug the 10 into this and see what we get. And then we're just going to make this a piecewise and plug the hole with that. So let's see what happens if I plug a 10 into this. Okay, we get 10 squared. See if I got my arithmetic down this time. 10 times 10, and then plus 100, divided by 10 plus 10. So that's 100 plus 100 plus 100, which is 300. 10 plus 10 is 20, and that is 15, which means this hole right here is at 15. So I'm going to plug the hole by saying, you know what? Why don't we just let f of 10 be 15? So even though we can't plug a 10 into the original because there's a hole there, we're going to plug that hole by saying we're going to let it equal 15. So just as, so on paper, kind of as a piecewise, you would then, we usually just kind of make it a capital instead, and we would say, okay, so this is going to be f of s as long as s is not 10. And then if s is 10, we're going to plug that hole with a 15. So we'll do the regular function, and then at 10, we're going to plug the hole with 15. So it says define 10 in such a way that it extends it. So again, we're going to let it be 15, but that's in a piecewise function. So when you write that on your paper, it would be a piecewise function. And then this one is similar. Well, not really. This one is a piecewise. And what we've got to do here is make sure there's not a jump discontinuity. So wherever 2 is on the graph, I'm not going to graph the whole thing, but it looks like to the right, well, we can't graph it because we don't have A yet. So it looks like to the left of 2, we're at 6. So it's just a horizontal line at 6. To the right of it, we've got a parabola. So what we want to do is make sure that, say, the parabola is not down there, in which case we would have a jump discontinuity. What we're going to try to do is, so, oh, well, that's a solid line. Here's the y equals 6, that second part. What we want to do is make it so that our parabola meets up right there and maybe goes up or goes down. But that way there's not a hole, okay? So even though there's a hole in this second part, there's a hole there at 6, we want to make sure that this equals 6 if you plug in a 2. You see, that way they agree with each other. So essentially, let me just show you kind of how to do this in general. So whenever you have a piecewise, you need to check that breakup. Now, you also need to check the individual functions. The first one's a parabola, the second one's a line, so there's no individual issues. But what we need to do is make sure that at x equals 2, we need to make sure that this one is equal to the other one. So really, I'm just setting the top one equal to the bottom one, and I need them to be equal when x is 2. So let's plug a 2 in for x and see what we get. That would give me a squared times, not 6, times 2 minus 4a. You're not plugging them into a. A is what we're going to try to figure out. So we can divide everybody by 2 here, make our lives a little easier. So we have a squared minus 2a. I'm going to go ahead and move that 3 over to the other side because I'm going to have to factor here. So I need 2 things that multiply to get -3 and add to get a -2. So we're going to need the 3 to be negative and the 1 to be positive. So if I let a equal 3 or I let a equal -1, we should be okay. All right. However, I'm guessing one of those is not where x is greater than or equal to 2. So that is going to be the issue here. So I need to make sure that they meet up when we are greater than or equal to 2. So if you think about it, every parabola, well, not every, but you see how this parabola will hit the 6 twice. So we actually just figured out the 2 places where that happens. It happens at, or sorry, it happens when a is -1 and it happens when a is 3. So we just need to pick the one that will give us the right-hand side, because we're supposed to do this when we are greater than or equal to 2. So let's just try the 3. If I have 3x minus 12, so I'm just using the 3 for a, which I did not do, did I? Because 3 squared is 9. So if we let that be 9x minus 12, and then we let this one be 6, then we're going, oh, never mind. It just wants both of them. Let's just stick them both in. I was getting ahead of myself. All right, so, oh, no, I forgot what they were. -1 and 3. Oops. Notice I just put a comma in between them. And I doubt it matters if you put the bigger one first or not. All right, so this one is just says we have a continuous function. And we know that it's negative at x equals 8 and positive at x equals 9. So it says, what does the equation, or why does the equation f of x equals 0 have at least one solution between x equals 8 and x equals 9? And then it says illustrate with a sketch. So do not look at the answer choices here for now. I'm just going to kind of let you know what this is going to look like. So this is going to be using the intermediate value theorem. All right, so apparently my pen is still not working. Okay, so this is going to be using the intermediate value theorem. Intermediate value theorem. So first, let's recall what that says. So the intermediate value theorem, and I'm going to kind of write it how it relates to this one. So let's say that this is 8 and this is 9. It says that we know that we get some negative value when x is 8. So we get something down here. And we know we get some positive value when x is 9. Now, what the intermediate value theorem says is, well, let's come over here. This is f of 8, whatever that value is. This is f of 9, whatever that value is. So the intermediate value theorem says that if you have a continuous function, keyword continuous, and you have two values, so f of 8 and f of 9, it says that if you pick any number between f of 8 and f of 9, so how about 0? If you pick any value between there, it says that somewhere on the x-axis between the 8 and 9, there's some value c where f of c is equal to that value you picked. Okay, so somewhere between 8 and 9 is a value, some place that gets me the 0 I picked. Now, this makes perfect sense because how am I going to get from here to here without hitting the, in this case, 0? You can't, right? There's no way to avoid it. No matter how you draw this, it could happen a bunch of times. No matter how you draw it, if you have to go from f of 8 to f of 9 without picking up your pencil, you have to have crossed the x-axis. Okay, and again, I'm saying x-axis because in this case, we're concerned with it being 0. And 0 is the x-axis. So what this is going to tell me, what it tells me is because f of 8 is negative and f of 9 is positive, somewhere between 8 and 9 is a value that equals 0. So let's write that out. And here's how you would write that out, say, as a bonus question on an exam or something. You would say, I'm just going to say notice f of 8 is less than 0 and f of 9 is greater than 0. Since f of x is continuous, the intermediate value theorem tells us that there is a c between 8 and 9. I'm going to go to the top, such that f of c equals 0. So notice all the key points there. I have to point out that one is less than the value, one is greater than the value. Okay, I have to point out that it's continuous, and so the intermediate value theorem tells me that there is a c between the 8 and 9 such that f of c is equal to 0. Okay, so that's how this works, and it needs all of those pieces in order to make it work. And so again, we already kind of drew a picture there. So let's see what our answer choices are. It says it has at least one solution because all continuous functions have at least one 0. No. It equals 0, or it has at least one between 8 and 9 because it's continuous on the closed interval. And if this is any value between f of 8 and f of 9, so in our case, the 0, then there's a place C between 8 and 9 such that f of C is equal to your value. That is perfect. And so this one, oh, it also wants kind of a sketch. So the idea is that f of 8 was negative. So wherever f of 8 is, we got a negative value. So that's this one if you look closer. So notice that at 8, we got a negative value. At 9, we got a positive value. The only way to get from there to there is to cross the x-axis, in which case there is a place where there's a 0. Yay! All right. And again, that was the intermediate value theorem. And we are done.